Hello student to the Foundation of Classical Electrodynamics course. So, under module 2 we today going to discuss about the electrostatic potential, electrostatic energy, but before that we are going to calculate few problems related to electrostatic potential and then we are going to start the electrostatic energy. So, let us start today's class. So, we today have the class number 29. So, in the last class we calculated the electrostatic potential for infinitely extended wire for finitely extended wire, and from that we calculated electric field. So, today we will going to extend that calculation for another case, and this case is for uniform charge disk. So, we calculate the electrostatic potential for uniformly charged disk. So, this is the problem. So, we have a disk here. Suppose this is the disk, and let me draw the coordinates, and strip I can draw here. So, the problem is this is a disk which is uniformly charged with say surface charge density sigma, and then what should be the potential at some point, say over this axis. If I say this is y axis, and if it is say x axis and z axis. So, what should be the potential at some point here over y axis? Say the coordinate of this point, say p is equal to 0 y 0. So, over y axis I should find a potential for this disk, and suppose this disk is having a radius of a. So, this is say a, and charge density rho, uniform charge density I already mentioned. So, normally in order to do this problem we take a small section, a ring of this disk. This is the ring, and for that we calculate and then we are going to integrate. That is the normal strategy. So, this is the region for which I am going to calculate the potential energy at point P, and then I will simply going to integrate. So, this is the region, tiny region. Okay. So, suppose the from here to here this is say r, and from here to here this is curly r, and this is y. I already have. So, this is from here to here r, this is curly r, and this is y. So, the d phi at the point 0 y 0 is simply due to this region, the shaded region is 2 pi r if dr is a thickness dr and the surface charge density, that is the charge, total amount of charge, divided by 4 pi epsilon 0 and the distance from that is r. Mind it, r is in terms of x and y is x square plus y square whole to the power half. This is the value of the r in terms of x and y. And I can write it, I can simply write this in terms of the value. So, 2 pi and 4 pi will cancel out. So, I can simplify it. It is sigma and then r dr divided by 2 epsilon 0 and r is x square plus y square. So, x here, I mean in this case it is simply r square plus y square. So, I should write it r square because otherwise so better I write it simply r square. Okay, since I already defined r here. So, square r square and whole to the power half. Okay. So, now if I want to find out what is my full phi at the point 0 y 0, then I simply need to integrate it and then sigma divided by 2 epsilon 0 and then when I integrate it should be r dr r dr divided by r square plus y square whole to the power half. So, this integration is simple. So, I have sigma divided by 2 epsilon 0 and this integration simply gives us r square plus y square whole to the power half. And now I need to integrate this for the entire disk. So, the limit should be 0 to a. This is the limit. So, my limit here is 0 to a. To a. Now, this quantity is sigma divided by 2 epsilon and then if I put the limits then it should be a square plus y square whole to the power half minus y. Okay. And for minus, if I go to the opposite direction, if I want to find out what happened the potential in the opposite side, then the phi 0 minus y 0, so this value simply comes out to be sigma divided by 2 epsilon 0 and then a square plus y square whole to the power half plus y. So, combining these two, I simply have that phi at any point mod of y is simply sigma divided by 2 epsilon 0, and now a square plus y square minus mod of y. That is the value I have. Now, if I want to find out what is the corresponding electric field, that we also calculated. So, electric field is minus of divergence minus of gradient of phi. So, that value is simply E at 0 by 0 is the del phi and del y in the direction of j with the negative sign. And if I do, then this value seems to be electric field comes out to be sigma divided by 2 epsilon 0 and then 1 minus y divided by a square plus y square half the unit vector j. Now, we know the result for infinitely extended surface, right? What is the electric field for infinitely extended surface, that is known to us. So, if I now make this surface infinite, then for infinite charge surface, I simply have the limit a tends to infinity, because then it is infinitely extended, and if we put that, then the value of the electric field that I get is simply sigma divided by 2 epsilon 0 with j unit vector. This is the result we already figure out using the Gauss's law and also using the simple calculation. We find this result. So, this result again we figure out by calculating the potential. So, this part was left in the last class. So, I just conclude that, I just complete this. Now, the next topic that we want to discuss, which is today's topic, and that topic is energy associated with energy associated with electric field. So, when we have electric field, then some energy is associated with that, because against the electric field, if you bring a charged particle, we need to do some work, and that work need to be stored as the electrostatic energy. So, that thing we will going to calculate. So, the procedure is like this. To do the calculation procedure is like this, a very interesting way. So, I bring a charged particle from infinite. So, this is say infinite, and I bring a charged particle from q1 from infinite to some point. So, this is my charged particle q1, and I bring this charged particle from infinite to some point, say p1 in some domain. So, this is the domain where I bring all the charged particle. Then I do the same thing for another charged particle q2. This is the charged particle, and I bring this charged particle Q2 to P2. So, mind it, when I bring the charged particle Q2 to the point P2, the charged particle Q1 at the point P1 is already there. So, we need to do some work against the electric field that is produced by the charged particle Q1, which is already there in the P1 point. That is the thing we need to consider. Then I bring another charged particle, say Q3, and this is the P3 point where I bring, and again when I bring this charged particle Q3, already the P1, P2 is staying there. I mean the charged particle at P1 and P2 is already there. So, we need to do the work against that. So, that will be stored. So, now work done, if I calculate the work done, so the work done for Q1, that means to bring Q1 from infinity to point P1. So, the work done for Q1 is simply 0, because there was, so if I write this is W1, so that value is 0. Then the work done for Q2, that is W2, that value is not Q, but the amount of charge you bring multiplied by the potential that is created due to the presence of charge 1, and that will be exerted on 2. So, it should be 2 1. Try to understand that when the charged particle is here, it is producing some kind of electric field, or in other words some potential is generated, and against this potential we bring the charge Q2. So, that potential will be experienced by Q2, and that will be stored as a work, as a energy there. Then work done for Q3 is W3, and that quantity is Q3 is experiencing the potential due to the charge on Q3 plus potential due to the charge 2 on Q3. Okay. So, why this is okay. So, why the work done is Q multiplied by phi, Q multiplied the potential, I quickly show, so that there should not be any confusion. To work done, we know that the work force dot dr, and this is the Coulomb force. The force should be Q into E, electric field E, right, and again electric field E is associated with the potential with minus of phi. So, now work done is minus of Q, if I put everything together, and then integration, F is QE. So, Q is there. So, it is gradient of phi dot dr, gradient of phi dot dr, and I am taking the charge from minus infinity to some point, say r, to some point r. So, that means this gives us minus of Q, and this quantity is simply minus of infinity to, sorry, it is plus infinity to r. So, this is d phi So, that means it is simply minus of q potential at infinity minus potential at r. So, that quantity is simply q as potential at r, because we consider that the potential as infinity to be 0. Now, the total work done, so that is why the work done is q and this quantity. So, let us go back to the calculation. Then total work done, W is W1 plus W2 plus W3, which is simply 0 plus Q2 phi 21 plus Q3 then phi 31 plus phi 32, that we already calculated, that we already mentioned. Now, if I do the same thing in the reverse order, this is an interesting process I mentioned, that is why. If I do these things in reverse order, for example, before I am in this case we just bring Q1 first and then Q2 and Q3, but if I do in the reverse order, let us first bring Q3 and then Q2 and then Q1. Then, so if we reverse the order, that is bringing the particle in a different order in the reverse order, then W will be simply W3 plus W2 plus W1, and that is 0 plus Q2 phi 23 plus Q1 phi 13 plus phi 12. Now, if I add these two, so whatever we have here in equation 1 and this is equation 2. So, if I add these two by adding equation 1 and 2, so by making 1 plus 2, we have 2 W equal to Q1 then phi 13 plus phi 12 plus Q2 then phi 21 plus phi 23 and finally Q3 phi 31 plus phi 32. So, that quantity 1312, so that is the total potential experienced by Q. So, I can write it simply Q 1 phi 1 plus Q 2 phi 2 and Q 3 phi 3. What is phi k here? K equal to 1 to 3. So, phi k, which is 1, 2 or 3, is simply the total potential experienced by the charge q k, right. This is the total potential experienced by the charge q k. So, the W is simply half of q1, or if I write summation, then it should be qk phi k. K is a number of particle that you are having. So, this quantity in Einstein notation, so this is repetitive index. So, I have half qk phi k. So, qk, as I mentioned, qk phi k is a potential experienced by the charge qk due to the all other charges. Okay, so what happened for two charges? If I have only two charges, so simply for two charges, suppose these two charges are placed in the coordinate system into two different points. Say this is q1 and q2, this is r1 and r2. So, the phi 1 2 is simply q2 divided by 4 pi epsilon 0 r2 minus r1. So, what is the meaning of that? This is, mind it, potential experienced by q1 due to the presence of q2. So, the potential energy W1 should be Q1 multiplied by phi 1 2. So, it is simply Q1 Q2 divided by 4 pi epsilon 0 mod of R2 minus R1. This is the potential energy that we. Now, for a set of charge, this is for two charge I calculate. Now, for set of charge, say for a set of charge, what happened for a set of charge, say Q1, Q2, Q3, Qn. At point, these are at points for the set of charge, these at positions say R1, R2, R3, Rn, the total energy will be W equal to half of all the summation where I is not equal to j, then Qi Qj whole divided by 4 pi epsilon 0, then Rj minus Ri mod. Okay. So, this will be the value of the charge, this will be the value for the total energy when you have a number of points like q1, q2, q3 distributed at the vector at the location r1, r2, r3, rn, etc. And also you should note that this integration will be done for all the combinations of I and j, but I and j are not equal. So, I just exclude all the condition when I and j, because when I and j is equal, so we are try to find out the potential for the same particle itself. So, that we exclude, and then I am going to get a result for the total energy, and this total energy is associated with the set of charges at the sitting at the position r1, r2, r3, and then if that is the case, discrete charge, if that is the case, we should have the expression like this. So, this is the expression of the total energy when all the charges are placed in these locations. So, today I do not have much time to start something new. So, I like to conclude my class here. So, in the next class again we are going to discuss more about the potential energy, and then try to understand why the potential energy is positive. We will going to calculate and see that the potential energy should be positive, it should not be a negative value, and obviously, but we will see that and try to do few problems if time permits. So, with this note I like to conclude. Thank you very much for your attention and see you in the next class.